Binary subtractors. They are similar to the binary adders what we have studied previously. Instead, binary adders had sum as an output and carry as the other output. But in binary subtractors, we will be having difference as one output and binary or borrow as the other output. Okay, so let's study what the binary subtractor is, what are the main concept, how does it work, and where it can be used. A combinational circuit which performs the subtraction of 2 bits is called binary subtractors. Again, the binary subtractors are of 2 types: half subtractors and full subtractor. It has 2 inputs, as we can see from the logical box. The 2 inputs x and y from the minuend and subtractor, like how we had augment and added in binary adder. Similarly, we have minuend and subtractand. That is, the number which is subtracted is called as subtractand. For example, let's say if x minus y is taken, so y is subtrahend and x is minuend, and d is the difference. As we can check, x minus y, the output is the difference, that is the d is the difference of x minus y. And if there is a borrow, then we can give it as b, which is borrow. So how does binary subtractor works? The binary subtraction is having a circuit diagram which is very much similar to the binary adder, but the only difference is it has an inverter, as we can check out from this. Okay, so now let's study the truth table for binary subtractor. As I said, minuend is a and subtractand is b. That is, here in this case minuend is x and subtrahend is y. So let's study the variations. First output will be 0 0, that is 0 1 2 3. So let's study the difference, how we can find out the difference and how we can calculate. The subtraction is as follows: 0 minus 0, the difference is 0, and since there is no borrow, we can write down borrow as 0. Similarly, 0 minus 1. Now here the difference is 1, and since a is less than b, that is minuend 0 minus 1 is a negative number, so we have a borrow which is represented here as 1. Now let's check the other variation, 1 minus 0. Okay, this 1 minus 0 is having the difference as 1, and since 1 is greater than 0, that is minuend is greater than 0, we have the borrow as 1 minus 0, which gives 0. Similarly, the last 1 1, 1 minus 1, the difference is 0, and since the difference is 0, that is 1 and minuend and subtrahend both are equal, there need to be no borrow, that is no borrow is there, so we write here as 0. Now if we check the truth table for difference and sum, they both have the same output. Therefore, the difference can also be written as, let's check out the difference. The sum had the output as, this was sum and this was carry. The sum output was 0 1 1 0, and the carry output was 0 0 0 1. Similarly, we can compare the difference and borrow truth table. Difference is again 0 1 1 0, and the borrow is 0 1 0 0. Therefore, we can write down as sum equation is equal to the difference equation is equal to A XOR B. Okay. Similarly, for borrow, that is for this part, we can write, if we make the truth table, or sorry, if we make the K map, we can get the equation as borrow is given by A bar B, where the carry was given by AB, the borrow is given by A bar B. Hence we can see that A in sum is replaced by A bar in difference. So that is the reason we have XOR gate in the difference, as the equation is similar to the sum equation, and we have NAND gate for borrow with inverter from the manual. So now, since this was a 2-input half subtractor, now let's study the full subtractor, which is having 3 inputs. That is, one is minuend, the other is subtrahend, and the third one is the previous borrow. Okay. A combination circuit which performs the subtraction of 3 bits at a time is called full subtractor. A full subtractor has 3 inputs: X, Y, bin. Bin is what? The previous borrow. And the 2 outputs, one is D, that is the difference, and the other is B out, that is the borrow, current borrow. Let us check out the working of full subtractor. This is a circuit diagram. So if we work out 0, 0, 0, that is 1, 0, first first input X 0, second input Y 0, and we can check out this bin. This previous borrow is also included here. So 0 minus 0, which gives 0, and again Y, that is, sorry, X minus Y, that is 0 minus 0. So let's work out this to avoid any confusion. Let's say X is 0 from the first equation, Y is 0 and B is 0. So this minus this, that is 0 minus 0, the output is 0. Again this 0 is subtracted with this B, which is this B. Okay, 0, this 0 is subtracted with this 0, so we get the difference is equal to 0 and borrow is equal to 0. Similarly, let's work out for this 0, 0, 1. X minus Y, that is 0 minus 0, we get the difference as 0. Now the difference 0 is subtracted with the borrow 1. So 0 minus 1, since the answer is negative, we get a borrow, which can be seen clearly from this part. That is 0 minus 1, the difference is 1 with the borrow 1. Similarly, let's check out with this 0, 1, 1, which is the decimal 3. So 0 minus 1, the difference is 1 and the borrow 1. So we directly write the borrow as 1, as we already have got 1. Now the output of 0 minus 1, that is the difference of 0 minus 1, which is X minus Y is equal to 1. That one is subtracted with this one. So 1 minus 1, the output is 0. Or in short, if we work out as X equal to 1, X equal to 0, Y equal to 1, and borrow equal to 1. So 0 minus 1, the difference is 1 and borrow is equal to 1. This borrow is written here. Okay. Similarly, now this difference is again subtracted with the previous borrow. Made a mistake here, it should be 1. This difference is subtracted with the borrow here, that is the difference of 1 minus 1, this difference minus this one, it gives the answer as 0. That is the final difference is 0. So this is working for the full subtractor. So now 4-bit adder subtractor, that is a combined circuit which we can have a circuit which can work as an adder as well as which can work as a subtractor. Now how the circuit can be designed, let's check this one. These are full adders, full adders, full adders, full adders. As we had carry system for full adders in the previous topic we have studied, the same way we have the carry. Okay. Now, as these are the XOR gates, we know XOR gate works as a buffer if one input is if one input is 0, and XOR gate works as an inverter if one input is 1. That is, if one of the input of the XOR gate is 1, the output will be the inverted output of the second input. For example, let's say if A is equal to 1 and B is equal to 0. Since one input A is 1, the output of XOR gate will be the inverted or the complement of the second input, which is B. So if A is 1, so to avoid this, let's work out. That is, let's say this is a XOR gate. If this is 1 and this is 0, since one of the input is 1, the other input is 0, the output of this XOR will be the inverted of the second input. That is, the output of the XOR will be 1. Therefore, when input is 1 to XOR gate, it acts as an inverter. Similarly, if we make a control line here as M and we give it as 0, the same output will be here and it will be as an adder. If we make this control line M is equal to 1, it will give the inverted outputs of the second input, and those inverted output will act as a subtractor. So in short, the 4-bit adder and subtractor can work as an adder when we have the control line as 0, and it can work as a subtractor when we can make the control line as 1. So we need minimum 9 number of NAND gates to implement full adder and full subtractor, and we need 2 half adder to make 1 full adder, and we need 2 half subtractor to make 1 full subtractor. As I have shown that the control line M, this is the control line. If this is made 0, which is written clearly here, if this is made 0, the circuit is an adder, as XOR gate acts as a buffer when one input is 0, and when M is equal to 1, the circuit becomes a subtractor. That is, when one of the input to the XOR gate is 1, the circuit acts as a buffer. The C and V are 2 outputs, where C is a form of carry and V is a form of overflow. If V is equal to 0 after an addition or subtraction, then no overflow occurred and the n-bit result is correct. If V is equal to 1, then the result of the operation contains n plus 1 bits. The same can be seen clearly in this diagram. Let's move on to binary multipliers. What exactly are binary multipliers? The multiplication of binary numbers. Binary multiplier itself says that it involves the multiplication of 2 numbers. So the multiplication of binary number is performed in the same way as the multiplication of decimal numbers. If we take the multiplication of 2 numbers, the multiplicand bits are B1 and B0. The multiplier bits are A1 and A0. Then the product is given by C3, C2, C1, C0. Let's study the multiplier circuit here. The multiplier circuit, as we can see, multiplier circuit uses NAND gate, as the function of the NAND gate is to have the multiplication. Like A0 B1, the output for this NAND gate will be A0 into B1. Similarly, the output for this NAND gate will be A0 into B0. So the 2-bit multiplier circuit, that is 2-bit by 2-bit multiplier circuit, works in the form of half adder. That is, it will give a carry when it has a carry, and if there is no carry, then it gives us the 0 carry.